Okay, so let us continue from the last lecture, right. So, let us go ahead and basically look at the axisymmetric flow properties, and then we will go over go over to the cone at the angle of attack, right. So, just to kind of remind ourselves what we did last time, right. So, we were looking at the cone, right. This is the cone surface, right, and okay. So, this is essentially a solid cone, right. And then we looked at the shock structure, okay. If we have a cone, if you have a supersonic flow coming onto the cone like that, okay. So, so basically we try to understand, okay, what the geometry definition looks like. The geometry is important. Why? Because that is the geometry of the shock itself, right, and its orientation with the free stream decides whether this is a 2D flow or a 3D flow. Okay, because if you look at this here, if you look at this shock structure over here, now this is going to be pretty much the same even when it is at an angle of attack, okay, with the free stream. But then in that case, however, we will consider the flow to be 3D. In this case, when it is the shock, the cone and the is in line with the free stream, then it is axisymmetric. Okay, then it is a quasi 2D flow, which we have studied, conical flow, right. So, that is the reason why it was important to kind of understand the geometry of it and so on and so forth. Okay, so let us go ahead and look at the okay. So, we started with this. So, let us now go and look at the basically the shock structure. Okay. So, here we are. Okay. So, this green thing here is our cone, right, and the red one here is our shock, which is happening. Both these have the same vertex, and this is the free stream that we are looking at. Okay. This is the free stream. So, in this case, okay, so say we have a streamline like that, it comes and it will deflect, right. We have something like this. Now, what we will do is, like we just did earlier, we will drop. Now, we will basically look at another cone within this cone, right. So, these are all all these. Now, when I draw this dark green stuff here, this is again another cone within this red one, right. And so if I draw a radial line, so I am going to basically draw a radial line from there. So, what I am actually doing here, okay, is that I am drawing this radial line, and this dotted basically means that it is happening inside this red cone. Okay. So, basically, so we have this surface of the surface of a cone like that, right. Now, within this surface, okay, within this cone surface shown by the red, I take a smaller circle, which is shown by this dark green circle here, right. So, this is inside. Okay. So, I drop a radial line from the vertical line, okay, within the cone to to which intersects the streamline here that you can see. So, this is the part of the streamline which is going inside the cone surface, okay, and finally deflects. So, then here basically I drop this dotted yellow line. Okay. So, that is essentially inside the cone surface, which intersects the cone surface, the streamline here, okay, and it is actually on this, and it is actually on this green green cone. Okay. All right. So, I'll draw one more. Okay, I'll draw one more. So, this is yet another cone. okay, and I draw one more I drop one more line, and then what we see here is again it crosses this the streamline at this point, and then I see something over here. Okay. Now, the reason we are doing this, because as we did in the last lecture, is that this is a 3D flow. Okay. So, the way you look at it, okay, so the plane in which you are looking at, okay, one should become comfortable with that, because this is the 3D picture that we are looking at right now. Now, if I look at this thing, okay, if I look at this whole picture through the base of the cone, I will see something else. When I look at the shock structure through the vertex, okay, through the vertex, then it looks something else. But it is important to familiarize ourselves, with the different views of this. Okay. So, now basically, so these points, okay, so these points are in 3D space, as you can see, right. So, all I have done is I have basically, this is my say in perpendicular, about this I have my cone. So, I have essentially, okay, I have essentially dropped, okay, 2 radial lines. Okay. I have dropped 2 radial lines. I am not saying anything about the phi angle or whatever. So, I have dropped these 2 radial lines, and what I would like to see is, if I were to look at the base of the cone here, where these 2 points would lie. So, what I would do then, these 2 points, okay, these 2 points on the streamline, okay, lie where on this base, on this xy axis, or in this plane surface, xy plane. Okay. So, if I see here, so if I can say basically the streamline is moving from here to here, right. So, the streamline moves from this point, shown by this filled circle, to this arrow. So, the streamline moves in this direction, and in this movement, or this positioning, is translated onto this plane, okay, into this plane as such. So, in this plane it is moving from here to here, right. So, similarly we can we can look at various other streamlines, and we will see how that look. Okay. Now, so what is important to see here is that we have these streamlines, okay, which encounter this shock surface, okay, and then they deflect. Okay. Now, similarly, we will also have flow or streamlines which will go on the surface of the cone, right. So, and if you remember right, okay, the on the surface of the cone, while we did the problem, okay, on the surface of the cone, basically there is only the radial velocity v theta is 0, right, if you remember right. So, on the surface of the cone, however, so we will have these straight streamlines. So, essentially you can think of it that you have this cone, okay, you have this cone and you have the flow, you have flow coming in, and it just goes out in all directions equally symmetrically about this particular point, about this surface. So, here is my cone, okay, here is my cone, and I have flow coming in. So, I have a shock wave. So, some of my streamlines come here and deflect, right, and then I enter here and I encounter the shock and I encounter the solid cone. So, then I just come there and move uniformly over the cone and move along its surface. So, basically these are all straight lines. Okay. So, we have straight streamlines which come which go on the surface of this cone, right. Now, let us look at the 2D picture of this. Okay. As you know here, okay, so this part here, okay, so this part here is the green part is the cone, right, and the red is basically the red is basically the shock wave. Okay. Well, blue is the section which we were using, we are not using that here. So, I mean, it is just a reference. You basically this entire place is filled with the shock wave. Okay. So, now in here how would these lines look? Okay. I am just trying to look at it. If I were to look from here, what would these look like to me? Okay. So, if I look here, so if you these will be all translated into lines like this, okay, on the 2D face here. Okay. So, therefore, in this particular case, okay, these two dotted yellow lines that I have, these are basically lines of phi. Okay. And if you remember, right, so see here basically about the vertex, okay, about the vertex I have a symmetric flow happening. So, if you remember from what we did regarding the conical flow, right. So, there was not any change in the phi direction as far as the flow is concerned. Okay. So, therefore, there were no changes in properties in the phi direction. Okay. And VR, so properties were constant along the radius here, along the radial line. Okay, properties are constant over it, and they vary only in the theta plane. So, if I change the theta this way, okay, in this plane it will change. So, therefore, the only dependent variable out here is theta. Okay. All right. So, looking at this picture here. Okay. So, let us now look at what exactly is happening when we talk about the 3D flow or conical flow at an angle of attack. So, essentially this is an axisymmetric case. Okay. This is an axisymmetric case. So, if I will just sort of remind you here. So, you have streamlines like this. Okay. You have streamlines like this, and these are the streamlines on the surface of the cone. Okay. So, keep that in mind and let us go and look at this. So, what exactly is happening in this particular case? So, we have this. Okay. We have this this surface, this is a cone, this is a shock wave which is on the sitting on the cone, right. So, what is this? So, what we have actually here is that this, now if you look at this, this is the free stream. Okay, this is the direction of the free stream, and you can see that the z axis or the line of symmetry, right, the line of symmetry of this cone and shock structure is making an angle of alpha with the free stream. So, this is essentially the angle of attack. So, this is the angle of attack. Okay. Now, so if you look at this picture here, so this dotted black line is essentially extending the free stream direction. Okay. Now, it is important to look here and find the difference between this, okay, this and what we just saw, which is the axisymmetric case. Okay. So, clearly now if you look at this, okay, now previously what we saw is that now if you now free stream here, okay, now my axis system would be to the free stream with a certain angle of attack. The lines of symmetry of the shock and the physical cone fail to coincide. Okay. So, what is important to note that the obviously the geometry of the cone, it is a physical cone, that remains the same, but the flow around it is no more symmetric, right. So, the flow is asymmetric and due to the inclination of the cone, and what we mean to say is now we do actually have one more parameter to take care of, which means that this is a another increase in dimension. Okay. The free stream. right. Now, if you look at the free stream and about that, okay, try to see how this shock is located, how the shock looks like with respect to the free stream. Okay. So, look first of all, for example, look at this red plane, okay, red plane and the shock structure, and look at this conical shock with respect to the black dotted line here. You can see the asymmetry in it. Okay. And then just compare that, okay, and similarly, and also compare it that if in fact the free stream was along this dark black line, okay, then what would the free stream be seeing? Most importantly, what would the free stream be seeing in that case, right? So, look what the free stream is seeing now, and if the free stream was along this dark black line, then what it would be seeing. Okay. So, if you look here, okay, this dotted line, okay, so you can see that basically in here, okay, the symmetry is lost. Okay, the symmetry is lost. So, we will not have flow coming in here distributing equally in all directions and move along the surface of the cone. We are not going to have that, right? We are not going to have that. So, we had streamlines coming in, straight streamlines coming in and deflecting and going past the shock structure here. Okay. Now, these are going to be curved here, they are not going to be straight streamlines. Okay. Now, let us look at this. So, here basically only for the, so the way the cone is located, only two streamlines right at the top of the cone and at the bottom of the cone, right, they will be straight sort of straight lines, okay, and they are the ones which will guide along the top and bottom surface of the cone. Okay. The rest of it, now if you see, if you think of the cone, so you have this, you have this cone here, right. So, you have the free stream, right, free stream which comes, and then from the bottom of the cone it moves to the, it will curl around the, what it will do, the flow will come here, if you look at this free stream, it will come here, okay. It will meet the shock, the solid cone here, it will curl around the bottom and come up to the top surface. Okay. So, what it will do is, the free stream say comes here, if I am looking at say this region here, it comes here, it will curl around the bottom and move to the top of the cone. Okay. So, now this, okay, let us look at some of those streamlines and see what I mean by that. So, basically what is happening is, it is coming from the bottom, curling up and coming here. It is coming from the bottom and curling up and coming to the top, coming from the bottom, curling up and coming to the top. Let us do that again. Okay. Let us look at this again. So, this is my angle of attack, etc. And then, so we have these two streamlines will of course be along the cone surface, okay. And then you have the streamlines on the rest of the surface, which will be curled streamlines. Okay. Now, if you remember, if you just try to recollect what we did one slide back, if this was axisymmetric, all these lines, all these curved lines, there would be no curling from the bottom to the top, there would not be. Okay. They would all just be straight lines like this. Okay. So, in here, so I have a flow coming in, right, like that, but you have so for the axisymmetric case, I encountered a cone right here, and I distributed, equally in all sides, and I started going this way. Okay. Instead here, now I come here, my cone is like this, my cone is like this instead of being right in front of me. My cone is not symmetric to me at all. So, I just moved just for the top and bottom surfaces, there are one straight lines, and then as I try to move, I go from the bottom and curl up and go to the top. Okay, that is what the streamlines are showing. Okay. And okay, yeah, well, some just trade names. So, this is the, when it comes from the this is the windward side. Okay. So, windward side, it goes from the windward side to the leeward side. Okay. So, well, this is, I guess, you know, you will probably recall this from your geography definitions back in school, because the side of the mountain which receives the wind, that is called windward, and the other side is called leeward, right. So, here, so basically you, because of the angle of attack, so you have the cone this way, because of the angle of attack you can see you have the free stream here. So, that will kind of reach the bottom part, which is so the bottom part is receiving the free stream, and then that curls around and goes to the top. So, this is just a trade name. Okay. So, if you okay, so that's that, right. So, essentially if I were to look at this, so I think it's important now, so that we will kind of deliberate as to what exactly is going on here. Okay. So, now if we look at this, okay, now in the axisymmetric case, okay, what are the velocities that we had? We had a VR, okay, we had a radial velocity in the direction of the radial direction, and we had a phase theta, right. We had that. We did not have any V phi, because it is axisymmetric. In this case, we have a VR, we have a V theta, and we have a V phi. We have all of that. Okay. So, why do not we just sort of understand, why do not I use the board and try and show you what I am trying to say over here. Okay. Okay. So, if we this is something that we have done last time, right. So, this is okay. So, if I do this, so this is my basically this is my z direction, right, and this is the radial direction, okay, and this of course is in the phi. Okay. So, the phi here is of course out of the plane of the board. This is by this time hopefully you understand what phi means. Okay. And theta is of course in this plane, if I look at it in a plane which is perpendicular to the z, x and y axis. Okay. So, and this was our free stream. Okay, this was our free stream. So, in this particular case, okay, let us look at, so we will have a shock structure somewhere. Okay, we have a shock here. So, we have a shock here somewhere. Okay. Now, let me just take a radial line. Okay. Let us just take a radial line. Okay. So, this is a radial line. Okay. So, what sort of velocities are we looking at this here? So, what sort of velocities are we looking at? What we are looking at here is radial, okay, and that. Okay. So, basically these are, this is the velocity that I am, velocity component I am looking at when I am looking at the axisymmetric case. So, essentially now also there is no property variation in phi direction. Okay. Now, the properties remain constant along a radial line, they however change as we change our theta. Okay. So, this is something we do. So, so in this particular case r and z are independent. Okay. So, we have only one dependent variable, which is our theta. Okay. So, now let us look at the same picture. Okay. So, let me look here. Okay. Let me make this a little short. Okay. So, here, okay, let me look at the same picture. Okay. So, now this is our free stream, okay. And now what we have here okay. So, what we have now, this is the z, okay. This is the z. So, if you look at this, okay. So, this is my z axis, okay, and so this is my angle of attack. Okay. So, this is how it looks like at this point of time. So, again I have shock waves and so on and so forth. Now, again I will again draw a radial line. Okay. I will draw again a radial line. Okay. So, if I look at this, say I will draw a similar kind of a radial line. Okay. Okay, I do this, then what sort of velocities are we looking at? We are of course looking at we are looking at v theta, we are looking at that, but we are also looking at a v phi. Okay, we are also looking at, this is my phi. So, in this case you will have to see that I am also looking at a phi direction. So, in this particular case v phi is not 0. Okay. So, essentially if you look at this, okay, so if you look at this particular point, okay, so I do have a change of properties if I take my radial line, you know, in if I give my radial line a deflection of some phi in this direction, in this phi direction, right. So, earlier case, if I removed a radial line about, you know, this central line, you know, in like that, I would not see any changes. V phi first of all here is 0, this is for the axisymmetric case, and so any property change, there is no property change in the phi direction. Here of course, that is not so. Okay. So, here v phi is finite, okay. V phi is finite, okay. This exists, okay. And of course, so del phi is also finite, del phi is also finite. Okay. So, this does not go to 0. So, this is in terms of what sort of velocities we would be looking at. Now, also like we've just seen, right, we've just seen that we will have you know, straight streamlines over here for this particular case, okay, for the axisymmetric case, okay, straight streamlines on the cone surface as well as here within the shock and the cone, whereas here we will not have that. Okay, we had streamlines which we saw something like this, right. These were the streamlines which were moving like this, so on and so forth. Okay. So, this is also important. So, they were curling up from and moving, and except we had these two streamlines which were moving on top. Here on the other hand, if you look at this, so on the surface we would have something like this. Would have something like this. Okay. So, that is basically which is giving us the slowly you can see the difference between the two cases. Okay. All right. Now, the next thing is if you remember the Taylor-McCall equation. Okay, let me sort of write that down. Okay. So, if I write this down, okay, not the Taylor-McCall, actually the Crocos theorem, sorry. Okay. So, now if I have the Crocos theorem, right, if you look at the okay. Okay. So, now if we this was our Crocos theorem, right, and we considered adiabatic and inviscid, okay, and as a result of which our delta S was isentropic. So, delta S was 0 and adiabatic and inviscid. So, our enthalpy was 0. So, and that meant that this was automatically irrotational. Okay. So, which was in this particular case. Okay. So, in this particular case this was this irrotational. Now, important thing is, if you look at these two pictures here, okay, does this flow out here? Does this flow out here look irrotational to you? It does, right? These two flows look very different. If you look at the two cone structures here, they look very different, right? Now, irrotational. Now, does this look irrotational to us or not? Okay, we use this, of course. So, we have adiabatic, inviscid, etcetera, etcetera. So, we got from here we were able to say, since these two go to 0, so automatically it is irrotational. So, this was a statement that for axisymmetric case here, okay, the flow is irrotational. So, if you look here, since in this case, since V phi is 0, okay, V phi is 0. So, this del cross V in this case is 0. Okay. So, essentially what we are looking at is that the velocity in a plane which is perpendicular to the xy plane, which is the cone surface, in this particular case. So, in that in this plane, okay, whether del cross V, okay, del cross V is 0. So, this is irrotational in this particular case. But look at this here, look at these here, clearly this does not look like it is irrotational, right. So, the flow we do not have straight streamlines, we have streamlines which are curling, okay. Also streamlines which are between the shock wave, okay, between the shock wave and the body, there are no more straight lines, okay. They are also curved lines, okay. So, what exactly, so how can we explain this? Okay. How can we explain this? Now, for a streamline, okay, now for a a streamline, okay, it has the same, it has a constant entropy. Okay. So, streamline will have a constant entropy. Okay. But okay, in this particular case, okay, now in here, okay, so when we have the shock wave, okay, now look at this sort of in this picture here, okay, the shock wave, okay, what is the angle of the shock wave angle? What is the shock wave angle? How does it look like in this particular case? Okay. So, if I may sort of go back to the diagram that we were doing over here, let us go back to that. Okay. This is the diagram that we had, right. Now, if you look here, okay, this red, okay, plane here, okay. Now, it could have now a point on this, okay, a point on this green plane or on this light blue plane here, it can have a different phi. Okay. So, therefore, inside this shock wave, okay, now this is our, if you look at this dark black dotted line here, okay, that is the free stream. Okay, this is the free stream. So, about this if you look, okay, the shock wave angle is varying as we make different phi angles. Okay. So, if I make a different phi angle, so if I make a certain phi angle about the axis of this cone, then my shock wave angle will also change, which is not the case when we did what we did for the axisymmetric case. Okay. So, in this case the shock wave angle, okay, is also a function of the phi angle, isn't it. So, we have a shock wave like this, right. Now, however, now since this shock wave, right, is not symmetric, okay, about the z axis, okay, and if you look at the free stream direction, then every time you make a small change in phi, every time you try to do that, there is a change in the shock wave angle. Okay. The shock wave angle also changes every time you make a phi direction. So, therefore, phi, so theta s, okay, theta s, which is our common nomenclature, okay, theta s is a function of phi. Okay. Let us go back to the board and do that. So, if I were to do this, let me just say I will just draw, okay, say I am drawing this as a shock wave. Okay, I am drawing this as a shock wave. So, clearly this is a spherical surface. Okay, this is a spherical surface. I am just drawing it like that. So, therefore, in here, okay, if you were to look at this, the shock wave angle, okay, shock wave angle. Okay, if I were to use this, okay, so this shock wave angle, although I write it as theta s, okay, now that is a function of phi, that is a function of phi. Okay. Now, a single streamline, okay, a single streamline has a particular value of entropy. So, entropy is constant on a particular streamline, but in here when a streamline, okay, is going from one point to the other, okay, when it is going from one point to the other, then there is a certain increase in the entropy, right. There is a certain increase in the entropy, because when it is going from one point to the other, there is a change in phi, which means that there is a change in the shock wave angle, and if the shock wave angle changes, right, which means that the nature of the shock changes, isn't it? Isn't that what we have learned? Whether a shock is very strong or weak and so on and so forth, that depends on what? That depends on the shock wave angle, right. So, now, so as the flow comes in here, right, it goes within the shock structure, and I have a streamline, right, it is within the shock structure and is moving from one point to the other, okay, the theta s is changing. You understand what I am trying to say? For example, let me try to do this here. In this particular case, okay, so this is my shock, this is my shock wave. Okay, and I have a streamline which is say coming here. Okay. Now, as this moves, okay, as this moves within the shock wave. Okay. Now, there is no change in the phi direction. There is no change in the phi direction, which means that my radial lines, that all my radial lines are equally spaced. There is no there is no change in the angle in which those radial lines are located. So, if I take the vertex of the cone, all my radial lines are all equally fanning out from this particular point. Right. So, when I have this streamline, so a streamline comes, it moves in here, the angle of the shock does not change, right, angle of the shock does not change. So, therefore, it is constant entropy, okay, constant entropy, and hence we can use the Crocos theorem, del H 0, del S 0, and hence it is irrotational. Here though, that is not the case. If you come here, if you come over here, so if you look at the, if you come to the vertex, okay, you come to the vertex, then we have a shock structure which is developed, okay, and then I move from one point to the other. Now, when I move from one point to the other, okay, since right, this cone and the shock, okay, is not symmetric about the z axis. Okay. As I move from one place to the other, the angle, okay, of the shock with respect in the phi direction, you know, the phi, that changes, right, which means the shock changes, which is almost equal to saying that we encounter a you know, a different intensity of the shock, which is, I think that would be fair to say, right. So, I encounter a different like I said a different shock. Okay. If I encounter a different shock, okay, then essentially I will have a different I will have a different entropy, okay, and which means that I will have an increase in entropy, okay, increase in entropy as I move through the shock, and finite incremental finite increase in this entropy, okay, non-zero increase in entropy. So, and that basically means phi direction, right. Phi direction is, so when I have the streamline moving in the phi direction. So, therefore, in the direction perpendicular to this say okay, yeah, this streamline. So, if I have, okay, this is not a streamline, this is a radial line, sorry. Okay. So, whatever streamline I have a particular streamline like that. So, perpendicular to it, I do have a finite increase in the entropy. So, in here is not 0. So, delta S is not 0. Okay, if you look at Crocos theorem, in there is a finite change in the entropy, and that is the reason, because as the streamline moves from one point to the other, okay, there is a change in the azimuthal angle, which is the phi, okay, which in turn means that we are looking at a different strength of shock. With the theta s is different, if theta s is different, I have a different entropy attached to it. So, therefore, in here it is irrotational, because here right. So, here this is not equal to 0, it is finite, and therefore, we do have in this particular case entropy. It is irrotational. It is rotational and not irrotational. So, means that this is which means that this is in fact rotational. Okay. So, unlike in the previous case. Okay. Okay, I think we are sort of closing into this. It takes a bit of a while to kind of try to understand the geometry a little bit more, try to visualize that, and hopefully this will start making a little bit sense, as you think about this a little more. I think another suggestion would be, if you can make a like I try to do this using Scilab and PPTs and all that. So, you can try to make a model yourself, okay, try to make a model yourself, and then try to visualize as to what I am saying, and look at the shock and cone in an axisymmetric sense as well as an asymmetric sense, right. Okay. So, let us ask one more time, if I look at these here, okay. If I look at this cone, okay, if I look at this cone out here, what do you think will be, for example, in here I have these streamline. Okay. So, what sort of entropy am I looking at? What is the entropy from here to here, each streamline? Well, each streamline here, each streamline will have, say, S not S naught, say S 1, okay, S 1. Each streamline will have the same entropy. On one particular streamline, there is no, there is one value of entropy, right. Now, you move from this plane into another plane, which means you are changing your phi. So, this is also another way of looking at it, is that in this particular case del phi. Now, when we go ahead and use this in our equations, which we will do that hopefully in another couple of lectures. So, then you will see, because del phi is not 0 in this particular case, unlike here del phi is 0. So, anyway when we start doing the equations, these terms cancel out. Okay. So, here this is finite. Okay. This is finite. So, when we change the phi, then the change in the entropy is also finite. The change in entropy is also not 0. So, that is another way of saying that. So, that is another way of looking at the this entropy change in this particular case. Okay. Okay. So, of course, to sort of wind up slowly. So, in this particular case we have, so this we have an r and theta and z, which actually we okay, we have these coordinates, right. We have these coordinates for both these cases. Now, if you look here for the irrotational, the only dependent variable here is the del theta. Okay. These cancel out. Okay. Do not need that. So, we basically have one dependent variable. So, that is all, and then we will have basically two components V r and V theta. Okay. Here, of course, we have two dependent variables, okay, theta and phi, of course. So, theta and phi, unlike in the previous case. So, here of course, again d phi del phi is finite, V phi is finite. Okay. So, having sort of come to that. Okay. So, for conical flows, okay, for conical flows we use the Taylor-Macol equation, right. So, Taylor-Macol equation, and we solved for it. So, we will see here how what we are going to do in this particular case when we have an axisymmetric case. Okay. But before that, I want to sort of look at this geometry a little more, try and understand as to what is happening to the streamline once it goes inside the shock wave and why it happens and so on and so forth. Okay. So, again, if I were to look at, for example, this picture here, okay, if I were to look at sort of this picture here. So, which is this was for the symmetric case, this was for the axisymmetric case, right. And yeah, so this is for the axisymmetric case, and what I am looking for is, okay. So, this you can see that this is the it is important to see this over here. Okay. So, you sort of move from phi, okay, and so this picture looks like this, isn't it? This looks like it. So, if I look at the planar region here, and I sort of what I am doing is superposing this these flows, superposing all this on the cone surface onto this plane. Okay. If I keep a cone here, there is a flow coming, flow is moving all around it. I am trying to look at it from this face, I am superposing all that flow. So, if I were to look at this face like this, I would basically see the point move from here to here. So, I would see things move like this. So, this right. So, now in this particular case again what happens? So, if you have something like this, okay, so in this if I were to superpose this onto the so if I were to superpose this onto the plane, then what would I see? So, that is something I would be interesting to see. So, let us see if we can do that in the next couple of lectures, and we can sort of figure that out. Okay. So, we will do that. First try and understand the geometry, because the geometry is very important over here, and then we will slowly go into looking at the equations, okay, and hopefully by that time all of that should make sense. Okay. All right, I will stop there. Thank you.